one skill that I find actually pretty useful when thinking about calculus in general is the ability to draw a sketch of the graph of the derivative based on the graph of the original function. Let me show you what I mean. So let's say here's our original function. F of x looks something like this. Too flat. And I'll do my best. Drawing the same thing over and over again is not something I'm particularly good at, but I'll try my best here. So there's f of x. And I would really, really, really like to be able to draw the graph of the derivative of f of x as a function, which is how we're thinking of the derivative now, right? Well, we'll talk a little more about that in a minute, but basically the derivative you can think of as the derivative as a point or the derivative in general as a whole entire function. So if I want to graph the derivative, I'm going to try and look for, well, one way to think about it is actually think about a car driving along this. If we think about a car driving along this little route here, we are thinking about the slope of the road. So like these are kind of hills. So like if the car is driving right here, the car is driving down the hill, right? Down, and then the car hits the bottom of the valley, and then it starts going up, and then, right? So we can kind of think about the direction the car is driving, whether down or up, as kind of the slope of the tangent line or the slope of the graph. And as a reminder, the slope of the tangent line, I don't want to say is the derivative, is one way of thinking of the derivative, right? There's lots of different interpretations about what the derivative means, but the slope of the tangent line is one way of thinking of the derivative. What we're going to do is I'm going to draw this same XY axis directly below it, so things kind of match up. And I'm first going to identify kind of the peaks and valleys because they're the easiest places to know what's happening. So right here, the tangent line is horizontal, meaning the slope of the tangent line is 0. So when I go down to graph it on the corresponding graph, that's going to have a y value of 0. Let's use green. I never use the green pen. It's probably. So here I'm graphing the derivative, meaning a value of 0 for the. And similarly, right about here, tangent line is horizontal, and right about here, the tangent line is horizontal. So those corresponding spots on the graph of the derivative are going to be the places where the derivative is going to equal 0. Okay, so now over here, unless we'll label a point or two. Let's say over here at point A, is the derivative positive or negative? Well, what's the slope of the tangent line looking like? If I draw a tangent line there, the tangent line there definitely has what kind of slope? For sure negative. And it looks pretty steeply negative too. So that's going to be a relatively large negative value. Whereas if you move a little bit to the right before I get to that point there, at B here, that tangent line still has a negative slope, but it is less steep. So it's a less negative value. So if we kind of draw corresponding down here, at A, it's going to be fairly negative. And at B, it's going to be less negative. Maybe something like that. So we've got something doing this kind of deal. And then we're going to cross into being positive, right? After this point here, the slopes of the tangent lines are then positive. A little bit positive, a little more positive, kind of maybe the most positive right about there. So it might do something like this. And then after that point, it's still a positive slope, but becoming less positive. So this mostly positive here is then going to come back around and do like that to where it hits 0. From here to here, everybody look, right? From that place with the derivative of 0 to that place with the derivative of 0, all my tangent lines are going to have negative slopes. So my derivative is going to be negative all the way from here to there. So do something kind of like that. Right? A little bit negative, a little more negative. The most negative it could be and then less negative, 0. And finally, after this point, all of my slopes are positive, so it's going to come off and go something like that. Kind of cool. Definitely a useful skill, which we're going to use later today. Let's do 1 or 2 more examples, just have a little bit of practice. Sure. Oh yeah, this one definitely comes up somewhat frequently. Actually, before we do questions about anything I've done before we do another example. Cool. Stephanie, you're also welcome to ask questions via chat or by saying words if you want to. Just probably freak me out if you say words. That's okay. Let's look at this example. Let's say we have the following function, and it looks like this. Let me try and draw it well. Draw it in a different color though. Do this kind of deal. So we're going to kind of go up. We're going to kind of level out for a second. Again, and then we're going to have a horizontal asymptote. Like that. Cool. That's my function f of x. And now I want to draw the derivative. And I do think if you ever have to do something like this, it is easiest to do if you draw the function, you're trying to draw the derivative, you're trying to draw directly below it. So you can kind of make places match up. So just like before, I'm trying to identify the places where I think the derivative is 0, aka where the horizontal tangent, or sorry, where the tangent line looks like it's horizontal. And to me, it looks like the only place really is kind of maybe right here, where there's my horizontal tangent line. It's actually kind of funky. This does happen sometimes. This tangent line crosses through the graph, which is totally allowed. It's just kind of a special point. It usually means you have an inflection point. That's okay. We're not talking about inflection points. Yeah, I just should say the thing because we're so right there. Thinking, okay, right there, my derivative is 0. And then, it looks to me like over here, the derivative is super duper positive. And then less positive, and then less positive, and less positive. So I'm going to start drawing my graph. It's starting out very positive, and then becoming less and less and less and less and less positive until I hit 0 at that point there. Now, after that point, my derivative is also positive. Sorry, my pictures, my drawing of my tangent lines is not going well. Apologies, but you can see, right? I will also say another word. The graph here is increasing, which also means the derivative is positive. That's actually the same sort of thing as the slope of the tangent line being positive, is the graph being increasing. So down here, my derivative, well, if my function is positive, sorry, my function is increasing, the slope of the tangent line is positive, the derivative is positive. So a little bit positive, and then we get to some place maybe right about here where the slope of the tangent line is the biggest the slope can be. And then after that, it's going to start to kind of level off. Maybe it's right there, right? Less steep, less steep, less steep, but still positive. So maybe right about here-ish is where the derivative is the most it can be. So we're going to kind of go up. We're going to hit some maximum. And then we're going up. I didn't draw that very well. Here's why I didn't draw that, or here's how I didn't draw that very well. I know that that's supposed to be the maximum, and so now I have to make a change of direction. I should have done it more like this. I should have been like, oh, I'm coming to a maximum, so I want to kind of level out, so it looks like that. And I kind of didn't prepare for that very well. Let's see if I can fix it. Probably not. Maybe. Sure. That looks kind of a little bit better. And then after that, my derivatives are still positive, but they're getting less and less and less and less and less. They're getting closer and closer and closer to being almost horizontal tangent lines. So my derivative is getting closer and closer and closer to being 0. And this is a decent approximation of what the derivative would look like. Question? So I will say this graph being increasing or decreasing has nothing to do with whether this graph is increasing or decreasing. This graph, so I'll point out, this graph I started with is always increasing, right? right? Yeah, always increasing. So that means this graph here, the derivative is always positive. So no matter what, my derivative here, which this is the graph of, is always above the x-axis. So f prime of x is greater than 0 for every x. But it doesn't tell us anything about whether the derivative itself is increasing or decreasing. But good question. Let's look at one more example, one or two more examples, and then we will move on to other things. So yeah, here's kind of a funky one. Here's my graph, or here's about to be my graph. F of x is going to look like this. Okay, there's my graph of f of x. And I will point out this graph doesn't have any places where the derivative is. There's nowhere where, well, that's a giant lie. Sorry. I mean, yes, okay, obviously there's some places where the derivative is 0. There's no like single, I just misspoke. I apologize. Obviously, there's some places where the graph has a derivative of 0, particularly from between here and here, right? Because right there's a whole horizontal tangent line. But what I really want to say is the slope of the tangent line here, well, if you have a straight line, the slope of the tangent line is just the slope of the line. If you try and draw a line tangent to this, you're going to get the same line you already have. So straight lines are their own tangent. Maybe a way of saying it. It's kind of weird. But the point is, the slope there is constant throughout. Slope of that tangent line or the slope of that line is negative something, right? It's definitely negative. So my derivative is going to have some negative value, some constant negative value to the left of this point here. So it's going to be negative like that. Now, at that point right there, where the graph is pointy, the derivative is not 0, undefined. Or another way of saying that is the function is not differentiable, right? If you've got a kink or a pointy point, or more mathematically formally known as a corner or a cusp, then the derivative is not defined. And so the derivative is not defined at that point. But then right after that point, the derivative is slightly positive, right? From here to there, you've got just some positive slope. It's not quite as positive as that negative slope there. So I'm going to draw the next part as being also a constant value, but not quite as high up. So from there to there, it's going to be some constant positive value like that. But again, at this corner here, derivative is undefined. After this corner, from here to there, the slope of the tangent line is 0. So from here to here, I get zero all the way. You know, it's kind of hard to see because it's on the axis, but oh well, there it is. Can't see that better now. And then finally, after that, the derivative is once again negative. I tried to make it so the slope looked like it was the same value as that slope there. So we're going to have the graph then being, and this would be the graph of the derivative. Notably, the graph of the derivative here is discontinuous because the original function was not differentiable everywhere. So if the original function isn't differentiable somewhere, that means the derivative itself will not be continuous at the place where it's not differentiable. Cool. All right, so definitely a skill worth practicing. We're going to use it a little. Yeah, we'll probably get to use it later today. Talk about stuff. Questions about any of these examples before we move on to totally different things? Yeah. Totally. So let's actually. So let me give you a specific example to kind of show you why. So let's say your function was f of x equal to absolute value x minus 3 plus 1. absolute values are always really excellent examples of functions that are not differentiable everywhere, but still continuous everywhere. So this function looks like the usual absolute value function, except I shifted it 3 to the right and 1 up. So this is going to look like the following. Usual V shape. Ooh, maybe okay, your usual V shape. Sorry, my drawing skills are less than usual today. There's your absolute value of x minus. And could we find intercepts and stuff? Sure, there's an intercept there. I don't actually care what it is. It's 4 or whatever. But the point is, this graph, and we're going to show it, but this function is not differentiable, bless you, at x equal to 3. Because there's a corner there, because there's a kink there, because, yeah, one of those two things, because it's a pointy point, as I would say. So how do we show it's not differentiable there? Well, we're going to use the limit definition of the derivative at a point. So I'm going to remind everybody, when I'm trying to find f prime of 3, it's going to equal f of 3 plus h minus f of 3. Oh, I forgot something very important. What did I forget? Right. What is this called? The what definition of the derivative? The limit definition of the derivative. There should be a limit as h goes to 0. So I'm just going to plug in these things to my derivative here, or to my function here. So let's see, f of 3 plus h is going to be, well, the absolute value of 3 plus h minus 3 plus 1, excuse me, minus f of 3 is going to be the absolute value of 3 minus 3 plus 1, all over h. Simplifying a little bit, you get the limit as h goes to 0. 3 plus h minus 3 is just h. So it's the absolute value of h plus 1 minus the absolute value of 3 minus 3 is just 0 minus 1 all over h. So that's the limit as h goes to 0 of the absolute value of h over h. Now, I'm pretty sure you've talked about this in class as well as in here before, but just so everyone knows why this doesn't exist, it's because the left-hand side and the right-hand side aren't the same. So we look at the limit as h approaches 0 from the right of the absolute value of h over h. Okay, we're approaching 0 from the right-hand side. That means we are positive or negative. Positive. So the absolute value of a positive number is just that positive number. So if h is like, 0.1, then the absolute value of h is still 0.1. Meaning we can just drop those absolute values if the insides are already positive. But then h over h is just 1. And the limit of a constant is just the constant. So from the right-hand side, the limit of this is 1. From the left-hand side, well, now h is slightly negative because we're approaching 0 from the left-hand side. And the absolute value of a negative number is the negative of that negative number to make it positive. So it's weird, but the absolute value of h here is negative h. That always seems to throw people off. It can be confusing, but just think about it. If h is like -2, the absolute value of -2 is negative 2, which is positive 2. That's how you change a negative to a positive. So then negative h over h is -1, and the limit as h goes to 0 from the left of -1 is, -1. And these two don't match, so this limit does not exist. But this limit was the derivative of f at 3, so that means f prime of 3 does not exist, or f of x is not differentiable at x equal to 3. It's a very long explanation, but that is the explanation for why when you have corners, or an example of why when you have corners like this, the function is not differentiable. The more kind of short way of saying it is the function has to be smooth to be differentiable, because essentially the slopes of the tangent lines from this side have to meet up with the slopes of the tangent lines from that side. The slopes here are like -1, slopes over here are like +1. And so since those slopes aren't matching up in like a nice, smooth sort of way, the derivative doesn't exist at that level. Another way you can kind of say it is, I could draw lots of different tangent lines. Like here's a fun. Whoa, wow. Can I draw lots of tangent lines? Maybe. Here's a tangent line. Here's a tangent line. There's lots of funky tangent lines that all have different slopes because that point is pointy. Okay. Cool. So let's remind ourselves maybe one, I don't want to say last time, but we're going to start moving away from the limit definition of the derivative. So I just want to point out the limit definition of the derivative. And I would say we kind of have two different versions of this. You might not want to write this down or something welcome to, but I just want to show you, for example. So for example, if you were trying to find f prime of 2, the derivative of f at the point 2, I know I haven't said what the function is. I'm not going to say what the function is. I'm just trying to kind of point out the definition. That'd be the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. But then we started to get more general. We said, well, I can do that really for any point A. We said f prime of A was limit as h goes to 0 of f of a plus h minus f of a all over h. And then we really said we'd really like to think of the derivative as a function. So instead of using a, we're just going to use x instead of a. It's really the same work. It's just a different letter of the alphabet. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. It's kind of funny though, because here we're definitely thinking of as like a as like a number, whereas here we're thinking of x as like a variable, but they're still both numbers. So these are ways of thinking of the limit definition of the derivative. So let's, how much time? Yeah, we got time. Okay. So we're gonna work through. So let's say, for example, we might as well just start there. Look at my function f of x is, fine, we got time. It's 5. Not a very exciting function. I can graph it. There's y equal to 5. Everybody, if you look at that graph, you should all be able to tell me what the slope of that line is. Right, 0, which means we know that the derivative of that function is 0. Now, you can also show it using the limit definition. Eventually you're not going to want to though. But, a constant function, the derivative is always 0 because the line of the function is always a horizontal line. But if you want to find the derivative, it's going to be the limit h goes to 0 of f of x plus h minus f of x all over h. Okay, here's where things get weird. F of x is 5. F of 2 is 5. F of 3 is 5. F of negative 17 is 5. F of anything you want to plug into the function is always going to give you an output of 5. So when I do this limit definition of the derivative, what's f of x plus h have to be? It's got to be 5. F of x is always 5 no matter what I'm putting in for x. And f of x is also 5. 5 minus 5 is 0. And 0, so here's kind of where the trickery happens, right? You might be thinking, well, James, it's looking like a 0 over 0, and you're not wrong. But we get to say, well, h is approaching 0. And so before we actually let h go to 0 and take the limit, we could say, well, h isn't 0. H is like 0.1 or something. And 0 divided by 0.1 or 0.2 or whatever number that's not 0 that you want, 0 divided by something that's not 0 is what? No, that's the other way. Something divided by 0 does not exist for sure, but 0 divided by 7 is 0, right? 7 goes into 0 how many times? 0 times, right? Let's double check. 0 goes into 7. Oh, that's the wrong way, right? That's not the right way. That's 0 divided. That's 7 divided by 0. We don't want that. We want 7 goes into 0. That's 0 divided by 7. And 7 goes into 0 times, and 0 times 7 is 0. And you subtract, and yep, that works out. And no other number would work, right? If there was a 1 up here or a 5 up there, not going to work out. So 0 divided by anything that's not 0 is just 0. And then the limit as h goes to 0 of 0, the constant is always just whatever that constant is. So it actually does work with the limit definition here. But you shouldn't do this ever, really. when you see a function that's a constant on its own, you should just say to yourself, I know that constant function. I would really like you all to think of that constant function has a horizontal line. And that horizontal line has a slope of 0 always, and that's why it's derivative of 0. That is really what I think of whenever I take the derivative of a constant function. Oh, that function's horizontal. That slope is 0. Okay, well, let's make it a little more interesting. What if our function now is 6x? Well, again, this one, I think you all could answer what the derivative is without actually doing any of the work. Right, if we graph that function, it definitely looks like a line whose slope is 6. Now, in fact, we could even add on a constant. If f of x is 6x plus, 3, the derivative doesn't change. Slope of the line is still 6. It just got shifted. So here, the derivative, I know it's going to be 6. I'm still going to show you the work just so you can see it. Plus, I'm building up to something. So there's also a reason I'm doing it, not just for the fun of it. So limit as h goes to 0 of f of x plus h minus f of x all over h. I do recommend that if you have to find something using a limit definition of a derivative on the exam, like you probably will have to on your next exam, I recommend writing this out before you start playing stuff. I think it's good to do. So when I do this, I get the limit as h goes to 0. Let's see, f of x plus h is going to be 6 times x plus h plus 3 minus f of x, which is going to be 6x plus 3, all divided by h. And then we do the same sort of thing. We simplify. We get 6x plus 6h plus 3 minus 6x minus 3. And just like every other time we've been doing these sort of things, the things that don't have h's cancel out. So you're left with a 6h over h. And the limit as h goes to 0 of 6h over h. Well, the h's cancel. And the limit as h goes to 0 of 6 is just 6, as we expected. So the derivative here definitely is 6. And for straight lines, whether they're horizontal with a slope of 0 or not horizontal with a slope of something, the derivative is always just whatever their slope is. The exception, of course, being a vertical line. The derivative of a vertical line, well, it's not really a function, and its derivative is definitely undefined because the slope is undefined. And that's also true when you have vertical tangents. If you have a vertical tangent line, the derivative is undefined. Okay, let's look at a couple more examples. How many more examples do I do here? Yeah, sure. Yeah, we're good. Okay, so let's do f of x equal to x squared. And now things are getting real. It's definitely going to be 2x. I imagine you all know the pattern already. I want to show it to you anyway, just because I think it's worth the time. Yeah, let's say f prime of x is the limit h goes to 0 of f of x plus h minus f of x plus h, which yes ends up being the limit h goes to 0 of x plus h squared minus x squared all over h. We multiply this out and we get the limit as h goes to 0 of x squared plus 2x plus 2xh plus h squared minus x squared all over h. The x squareds cancel. Everything left has an h in it, so we divide by h and you get the limit as h goes to 0 of 2x plus h, which yes is going to be 2x plus 0. And you might already be aware, in fact, I know she talked about it on Monday, of the power rule. And the power rule says the following. The function x to some power, then the derivative is that power times x to the previous power minus 1. And I would really, I would like to take a few minutes of your time just to kind of show you why this is true. So, or actually, let me ask you all, did your teacher talk about Pascal's triangle in class? The answer is probably no. Okay, great. The Pascal's triangle is super cool. If you ever take stats, or if you've ever taken stats, specifically the probability section where you're talking about like the choose function, you might recognize Pascal's triangle. But if you don't, or later on when you take stats and you have to like do like some binomial distribution kind of thing, come see me and we'll talk about Pascal's triangle because it's super useful. But Pascal's triangle looks like this. Starts off with some ones, and then you add the ones together to get the term there, or you add the middle terms to get the next term. So 1 plus 1 gives me 2. And then still a 1 on the outside. 1 plus 2 gives me 3. 2 plus 1 gives me 3. 1. And then 1 plus 2 is 4. 3 plus 3 is 6. 1. And it goes on. 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on, forever and ever. The reason this is neat, well, I mean, there's lots of reasons it's neat. The particular reason right now that it's useful is check this out. X plus h to the 0th power is 1. Anything to the 0th. Well, any non-zero number to the 0th power. 0 to the 0 is a whole other indeterminate form. There's lots of indeterminate forms. X plus h to the first is 1x plus 1h. X plus h squared, as you've seen, is 1x squared plus 2xh plus 1h squared. And it will tell you that x plus h cubed is 1 times x cubed plus 3 times x squared times h plus 3 times x times h squared plus 1.
Factoring thing, if you have a big,
Factor.
gigantic factoring problem, you're just like, I don't want to deal with it.
Right.
Do that.
Right. And now it only kind of works for this where you have like something plus something or something minus, really minus is still plus, to a power, to a positive integer power. So, but the point is, right, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 2, 1, 1, 3, 3, 1, 1, 3, 3, 1. And the way you find the powers is the powers just start off with whatever your power is. So I start off with an x cubed, and then each term, the power of x is 1 less, the power of h is 1 more. So I would like all of you to take 30 seconds for me and write out what x plus h to the 4th is going to be. I'm going to start with 1 times x to the 4th plus, okay, I want you all to write the rest. Not terrible. Okay, so 1x to the 4th, and then do 1, 4, 6, 4, 1, so I'm going 4, x to the 1 less power, h to the 1 more power. And then 6, x to the 1 less power, h to the 1 more power. And then 4, x to the 1 less power, h to the 1 more power. And then 1, x to the 1 less power, x to the 0, so I'm not going to write it, and h to the 1 more power. This pattern always works. Kind of cool. Notably, if I go all the way down to like say x plus h to the pth power, here's what you're going to get. You're going to get 1 times x to the p. And then notice also that the second term in each of these is just whatever the next number is. So, right, in x plus h to the 4th, I use this row, and the second number was 4. For x plus h to the 5th, I would use this, and the second number would be 5. So every time we do this sort of expansion, the second term is going to be just whatever the power is that we're using. Right? X plus h to the 4th, you got a 4 there. X plus h cubed, 3 there. X plus h squared, 2 there. X plus h to the p is going to be x to the p plus p times x to the p minus 1. Oh, that looks promising. Times h to the 1st. And then lots of other terms that we're not going to care about. Let me write down what so plus, I don't actually know what the next number is. So I'm going to write some constant times x to the 1 less power times h to the 1 more power. And then lots of other terms all the way to the very last term is going to be h to the pth power. Okay, so check this out. If I want to find the derivative of f of x equal to x to the p, which I know you already know what it is, but it's still nice to believe it and not just have someone told you what it is. So a lot of time I'm going to try and show you things just so you can be like, yeah, that actually seems reasonable. So to find the derivative, we're going to use limit definition. The limit h goes to 0 of f of x plus h times f of x h limit h goes to 0 of x plus h to the p power minus x to the p all over h. Now, we just mentioned that x plus h to the p power is all of this trash. So that's going to be the limit h goes to 0 of x to the p plus p times x to the p minus 1 times h plus some constant I don't care about times x to the p minus 2 times h squared plus a bunch of other terms that all have higher powers of h. The next term has h cubed. The next term has h to the fourth, all the way until we get to the very end, which is going to be. And I didn't make a mistake. That's fine. I did not make a mistake. H to the p. And then finally, minus x to the p all over h. Okay, great. Everybody, what can I cancel? What's the only thing that I can cancel? Yeah. Or as I would say, the non-h terms, right? Here, wait, everything that didn't have an h canceled. Everything left has an h. So let's divide everything left by h. If I divide everything left by h, I get p times x to the p minus 1. H divided by h is 1. In the next term, some constant times x to the p minus 2. H squared divided by h is h to the first. The next term would have something with an h squared. Blah, 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 h squared. Plus all the way to the very last term, being h to the p minus 1. Because h to the p divided by h to the p. And now, if we let h go to 0, every term that has an h in it is going to go to 0. So we're left with p times x to the p minus 1. As we knew the answer was going to be, but it is nice to see the answer. Couple notes here. Thing one, the thing we have just done, proving in quotes the power rule. We have proved the power rule technically only for positive integer powers, because this formula for x plus h to the p only actually works if p is a non-negative integer. However, that doesn't take away from the fact that this power rule is true for any real number. So it is always true. I'm going to write this in two different ways. That if f of x is equal to x to the p, then f prime of x is equal to p times x to the p minus 1 for any and every real number p. Or as I would prefer to write it because it's more succinct, the derivative ddx, the derivative of what I'm about to write with respect to x of x to the p is equal to p times x to the p minus 1. This is a much easier way of writing. It means the same thing. Okay, great. So it's true if your power is positive, true if your power is negative, true if your power is a fraction, true if your power is some weird irrational number, true if your power is 0, true if your power is 1. In fact, it's kind of cool to see that the derivative of, say, like 5, and I am going to use this notation a lot, so you should get used to it. This just means the derivative with respect to x of whatever's over here. So the derivative of 5, well, we already know that 5 is a constant, derivative is 0. But if you want, you could apply the power rule by rewriting the. Now, you shouldn't do it this way. But I just want to point out that if you wanted to, the power rule would work. Because 5 is really 5 times x to the 0. And the derivative of x to the 0 using the power rule is going to be 5 times, well, x to a power, you're going to get 0 times x to the 0 minus 1. 0 times anything is 0, so the whole thing is 0. Cool. And it also works for, it works for everything. So let's do some examples. How much time have we got? Okay, I got time. So let's say we want to find, now we're going to do an example here that's going to include something that, well, yeah. So I'm talking to myself really. Let's say we have this. Let's say f of x equals x to the 10 plus the cube root of x squared plus 1 over x to the 5th plus 7. And I want to find f prime of x. Well, to find f prime of x, I would really like everything to look like x to a power. And currently it doesn't. I'm going to rewrite this as f of x. Don't write it as the derivative. You're not taking the derivative yet. Is x to the 10th plus the cube root of x squared is x to the 2/3 power. And 1 over x to the 5th is x to the negative 5th. And now these all look like x to a power, and I can just throw the power rule at it. So my derivative here is going to be x to the 10th is going to be 10 times x to the, you can write 10 minus 1, or you can just write 9. And then you're going to get 2/3 times x to the 2/3 minus 1 plus -5 times x to the -5 minus 1 plus the derivative of a constant is 0. Now we should do a tiny bit of simplifying. This is going to equal 10x to the 9th plus 2/3 x to the 2/3 minus 1. Well, 2/3 minus 1 is 2/3 minus 3/3, which is -1/3. And I would, instead of writing plus minus 5, let's write this just as -5 times x to the -5 minus 1 is -6, and that's our answer. When you take a derivative of a function using the power rule, the power of x should always get smaller. So if it was positive, it should be less positive. And if it was negative, it should be more negative. That's why the derivative of x to the -5 is -5x. More negative. Now I used a rule here that we haven't ever talked about, but it's kind of a rule that almost is like innately obvious to us when we use it. We took the derivative of all these things added together by just taking the derivative of each part and then adding the results together. Your teacher definitely mentioned this rule at the end of class on Monday, I think. Basically, the idea is that if you're taking the derivative of f of x plus g of x, it's just equal to the derivative of f of x plus the derivative of g of x. It doesn't matter if you're adding or if you're subtracting, the rule still applies. No one ever writes it this way. No one ever is going to be like, write down the derivative of this rule. But it's a rule we use all the time. So they're like, well, I'm just going to take a bunch of derivatives and add the results together. It is not similar to the product rule. It's much easier than the product rule. The product rule is a rule I have to actually think about using. This rule here, I never actually think about using. I just use it because it's, I don't want to say it's obvious, but it's obvious. Like it's a rule that after you do derivatives for like a few minutes, you're like, well, yeah, I'm just going to take this function, take it to the derivatives, add the results together, we're good to go. Let's look at another example. Let's say my function was g of x equal to 4x to the 7th plus 3 divided by the square root of x minus 5x squared plus pi to the 7th power. This is a very general piece of advice, but I want you to take it to heart. When you are finding the derivative or needing to find the derivative function, it is almost always in your best interest to simplify first. Here, I definitely want to write everything as x raised to a power. And I've almost got that, except the second term here, not quite. So I should really rewrite this. Since I'm not differentiating yet, I should still write g of x, not g prime of x. I'm not yet taking the derivative. Also, no half measure, right? We don't want to take like the derivative of parts of it and then not and simplify the parts. You either want to be simplifying or differentiating, one or the other, never really both at the same time. So rewriting this, it's 4x to the 7th plus 3 times x to the -1/2 minus 5x squared plus pi to the 7th. Cool. Now we can take the derivative. So what's the derivative of 4x to the 7th? Right, and you all just used the rule that we've never talked about, but you definitely knew how to use it. Where if you have a constant multiple of a function, you leave that multiple there and you take the derivative of the function and multiply them together. Right, what's the derivative of x to the 7th? Right, and 7 times 4 is 28. So really what you all just did there, even though you didn't know what you were doing, is you said the derivative of 4x to the 7th is really 4 times the derivative of x to the 7th, which is then 4 times 7x to the 6th, which is 28x to the 6th. That's a rule that we use all the time as well. If you have a constant multiple, what I usually like to say is constant multiples hang out. So if you have a constant multiple of a function, you take the derivative, you get the constant times whatever the derivative value is. For the power rule, it's really easy because you multiply the power by whatever's out there. Same deal here. You're going to get a 3 times a -1/2, so you're going to get a -3/2 times x to the -1/2 minus 1 is also -3/2. That's kind of just a coincidence. All right, the 2 comes down, you get minus 5 times 2 is 10 x to the first, which I'm not going to write the first power. Finally, plus, right, not 7 pi to the 6, 0. Be careful. There's definitely problems in your homework that are trying a little bit to trick you. They're really just trying to make you think, right? Pi to the 7th is a constant. How do I know it's a constant? Do I see any x's in pi to the 7th specifically? When there's a pi and there's a 7, I don't see any x's. There's no variables there. If there isn't a variable, the thing is a constant. Just to add on to that list, the derivative of the natural log of 7, I don't see any constants. I'm sorry, I don't see any variables, apologies. I definitely see the constant. Derivative of natural log of 7 is 0. Or the derivative of e to the 4th power is 0. Or the derivative of 1 over pi cubed, also 0. All these things are constants. If you don't see an x or whatever the variable you're using is, like t or u or whatever, you don't see that variable there, the thing is a constant and its derivative is 0, even if it looks super funky. I will point out one more time, we definitely use that same rule where we had a bunch of functions added together or subtracted together, and we took the derivative just by taking the derivative of each part and then adding or subtracting the results together. Okay. Yeah, I got time. So let's say we have something like this. H of x equal to x squared plus 3x times x to the 4th plus 2. We don't get, well, she did mention the product rule in class, right? On Monday, I think. I feel like I saw the notes. Anyway, well, regardless, you shouldn't use the product rule here, even if you wanted to, right? This is a problem that is super easy to multiply out, so we should multiply that. Sometimes you have to use the product rule, but not here. So if we just simplify this, x squared times x to the 4th is x to the 6th. X squared times 2 is 2x squared. 3x times x to the 4th is 3x to the 5th. And 3x times 2 is 6x. Then the derivative can easily be taken as 6x to the 5th plus 4x plus 15x to the 4th plus 6. And I guess I could leave it like that, even though it feels a little bit wrong. I would really probably rewrite it so that the powers were in descending order, but not a crime to not do that. I do want to point out, because it's really important, h prime of x is not just the product of the derivatives here. You take the derivative of this first part, which is 2x plus 3, and the derivative of the second part, which is 4x cubed, and then multiply it out, you get 6x to the 4th plus 12x cubed. And that is definitely not the same as that. So I want to point out h prime of x is not equal to the derivative of each part multiplied together. So it's a very common mistake people make when they're trying to think about taking the derivative of a product. You cannot just take the derivative of each piece and multiply it together. We have to use the thing called the product rule, which we probably won't get to today, but we might. We'll see. Simplifying is the name of the game. If you can simplify it, you probably should. For example, if you have a function like f of x equal to x to the 8th minus 7x squared plus x to the 4th all over x cubed. Sure, x cubed, yeah, why not? Well, you could, once you learn it, use the quotient rule here. You shouldn't. If you have a fraction where you have one term in the denominator, we can simplify this. I should definitely rewrite this as x to the 8th divided by x to the 3rd minus 7x squared divided by x to the 3rd plus x to the 4th divided by x to the 3rd. And then simplify each of those and rewrite it again as x to the 5th minus 7. Instead of 7 over x, I'm going to write 7 times x to the negative first, plus x to the fourth over x cubed is just x. And now we can just use the power. Say, oh yeah, my derivative is going to be 5x to the fourth plus 7 times x to the, what's my new power going to be here? Right, -1 -1 is -2. And the derivative of x is just 1. Right, y equals x to the slope of just 1. And I think this example is in your homework, but that's all right. I don't mind. Let's say our function was h of n equal to r times n times 1 minus n over k. Now, I think in the problem in your homework, they actually tell you what the constants are, but we should be able to look at the way this function is expressed and identify what one thing is the variable. So what's the variable? Is it r, or is it n, or is it k? Gotta be n, because I wrote the function as h of n. So n is the input that's variable, r and k are just constants. So when I differentiate this, well, before I differentiate this, I'm going to multiply it out. So I'm going to write this as h of n equal to rn times 1 minus rn times n over k. So r times n squared. Actually, I'm going to try to make my life even a little bit easier. If you're multiplying or dividing by a constant, it's really kind of nice to put that out in front. So, excuse me, I would rewrite this as h of n equal to r times n minus r over k times n squared. Now I can see the constant multiples, they're easier to deal with. So now, taking the derivative, the multiple of r hangs out, and the derivative of n to the first is just 1. So we get r times 1. You don't really need to write the times. Similarly, the minus r over k is a constant multiple, it just hangs out, and the derivative of n squared is 2n. That's our answer. If you wanted, you could rewrite it as r minus 2r over k times n, just to make it more obvious what the constant part out in front is. Yeah. Sure. Yeah, okay, I feel like, yeah, we should keep going here. So we're definitely going to get there, but it's after, before we get to the chain rule, we have to talk about some trig derivatives and the product rule and the quotient rule. So we'll probably get to the chain rule next week. Actually, well, we'll probably get to it next week, but before the end of class, I will leave you with a short example of the chain rule, just so that if you want to start, because I know there's homework to do, want to start working on those homework problems, you'll have an idea of how to approach it. So let's talk about some trig derivatives, specifically sine and cosine. Now, I know your teacher just told you what they were, at least I saw from the notes, it looks like she just told you what they were. Let me give you a little bit more background. This is where we're going to use that graphing idea I talked about before. So let's graph sine. So if I look at sine of x looks like this. Got a period of 2 pi, which I like to cut into 4 equal quarters or quadrants. And then has a maximum value of 1, has a minimum value of -1. And sine starts at the origin. And then at pi over 2 has a value of 1. And then pi has a value of 0. And then 3 pi over 2 has a value of -1. And then 2 pi, we've done a full cycle, and we're back to where we started. This graph looks like this. I could have just graphed it on Desmos, but it is a good graph. It is a graph I think all of you should be able to graph with relative ease. It's a good graph to be able to graph. So there's sine. Now we're going to graph its derivative, just like we graphed derivatives at the beginning of class. I'm going to draw another graph below it. And I'm going to kind of look at these 5 points. This point here, here. Okay, so let me ask all of you. At pi over 2, what's the slope of the tangent line? 0. So for my derivative, I'm going to get 0 there. And at 3 pi over 2, slope of the tangent line is also 0. I always look for the zeros first. It's just it's the easiest, to be honest. And then at the origin here, you might not know exactly, because you might not see this before, but it is true that the slope of the tangent line is 1. And by symmetry, if you know that this slope is 1, you can probably convince yourself that the slope here is -1 at pi. And then lastly, we've done a whole cycle. If you have something that's cyclical, it's going to repeat itself after the end of the cycle. So we're going to get back to where we started in the value of 1. And if you graph this thing, don't screw it up. That graph looks a lot like it is true, the derivative sign is cosine. And then you can keep doing this. Okay, well, I could also graph the derivative of that. If we graph the derivative of that, I think I have enough room here, probably. So now, keep going. I guess I could label these points here. Sorry, I'm doing a bad job of labeling things. Pi over 2, pi, 3 pi over 2, 2 pi. Now at the origin, the derivative is 0, or not the origin. At this point here, slope of the tangent line is 0. At this point here, the slope of the tangent line is -1. At this point here, the slope of the tangent line is 0. At this point here, the slope of the tangent line is +1. And finally, at the last point here, we're back to 0. And the graph of this, I would say the graph of this looks like my sine function, but I flipped it over. So that derivative of cosine, which is the second derivative of sine, is going to be negative sine. Kind of cool. Now we have enough information to finish the, so I don't want to draw any more of these, it's kind of annoying. But now I'll say, if my function is sine of x, the derivative is cosine of x. And the derivative of cosine of x, which is the second derivative of sine, is negative sine of x, which I will point out is equal to -1 times sine of x. And the reason I point that out is because, oh yeah, question, sorry, oh, sorry, thank you, yeah, you should just yell. Like, James, I can't see. Yeah, sorry about that. So yeah, function sine, derivative cosine is negative sine. And I know that the derivative of a constant times a function is just the constant times the derivative of that function. So just like the derivative of sine is equal to cosine, the derivative of negative sine is equal to negative cosine. And finally, just for completeness, the fourth derivative, which we write like this, I'll say more of that in a moment. Well, the derivative of negative cosine is going to be -1 times the derivative of cosine, which is negative sine. And -1 times negative sine is sine of x. When you get past the third derivative, we almost always write the derivative. Instead of writing 3 primes or 4 primes, you write a superscript with a parentheses around the number of the derivative. You do need the parentheses. That's kind of required. It's funky notation. If you don't have the parentheses, you mean like f to the 4th power. You need the parentheses to stand taking the 4th group. Yeah.
Wait, so is that what's the name of it? So it's like acceleration is the double derivative.
Well, I would say yes, there are physical interpretations of these derivatives. You can think of the first derivative of position as velocity. You can think of the second derivative of position as acceleration. You can think of the third derivative of position as jerk, which you probably have all experienced at one point in your life. If you brake really hard, the rate of change of your acceleration has changed, or your deceleration has changed. or if you really stepped on the gas and jerked forward, right? It's actually called jerk because it's what's happening. You are jerking either forward or you're jerking to a halt. But and then there's a name to the fourth one. I don't remember what it's called. It's something even funkier. I was just reading it the other day. I was like, oh, that's weird. I've never seen that before. Yeah, there are names for these things. There's not always a good physical interpretation once you get higher than the fourth derivative. But yeah, but there are definitely, you can take any number of derivatives that you want, provided the function allows for it. Most functions are usually lots of differentiable, meaning you can take many derivatives. Sine and cosine, you can take derivatives all day long, and you're just going to cycle back on yourself. So after the fourth derivative of sine, you get back to sine. Then the fifth derivative would be cosine, and the sixth derivative would be negative sine, and so on and so on and so on. It's kind of neat though that sine has this cycle. So sometimes some people will ask you some funky question, like I'm going to write it in a different way instead of writing it. So I could say I'm going to write like this: if f of x is equal to sine of x, what is the, say, I don't know, 97th derivative? Or if you prefer, you could say the d97 dx 97. That means the 97th derivative of sine of x. Okay, well, what's the biggest multiple of 4 that's less than 97? Is it 96 or is it 94? It's 96. I know 100 is a multiple of 4, right? 25 times 4 is 100, and 100 minus 4 is 96, so 24 times 4 is 96. So I know that I can do 96 derivatives of sine and get back to sine. And then if I do one more derivative of that, it's going to be the next one on the list, which is cosine. Kind of a weird problem, but people do ask. All right, so derivative sine is cosine, derivative cosine is negative sine. We'll get to the other trig derivatives probably next week when we talk about the when we get to them, because you need the quotient rule. We'll talk about the other trig derivatives. Actually, that's not entirely true, but it's. I will also just mention, if you are really interested, there is a way of finding the derivative sine and or cosine using the limit definition of the derivative. But I don't think your professor is particularly interested in talking about that, so it's also not super necessary. That's how I like to think of it. You think about the derivative sine, you can graph it and see like that. Yeah. Which way to go? Because she talked about the derivative e to the x and of natural log of x as well, right? Or at least I should say, I think she did because I saw it in the notes. We'll get there in a minute. Yeah, I guess we should. Okay, fine. So I will point out that the derivative of e to the x is e to the x. It's kind of cool. It's actually really cool. The way I would maybe think about this is thinking about the graph. Here's the graph of y equals e to the x, or f of x equals e to the x. And it's true, and it's kind of weird that on this graph, the slope of the tangent line is always equal to the y value of the graph. So for example, right here at the point 0, 1 on the graph, the slope of the tangent line is 1. And any other point on the graph, slope of the tangent line is equal to whatever the y value of the point of tangency is. So just to kind of make it probably look not as nice, if I go over to the point 1, e, the slope of the tangent line there, if I can draw it with any kind of decency, the slope there is e, approximately 2.7. But yeah, I think my picture might convey that idea. Later on, once we have talked about either implicit differentiation or the chain rule, we're going to revisit this and I'll actually show you really why the derivative e or how you can calculate the derivative e to the x and e to the x. But for now, we're just going to kind of accept it, even though I don't love that. And then what I will say more generally, because it looks like it's coming up, and again, I want to show it to you more, but I feel like you might want to know it just so you can work on your homework. The derivative of 6 to the x is 6 to the x times the natural log of 6. It's kind of funky, but I will point out more generally, there's two formulas for the derivative of a exponential function. There's really only one, but I'm going to say it like there's two. So first of all, exponential functions characterized by not having x to a power, like x squared or x cubed or x to the fourth, but having something raised to the x, where the variable is in the exponent. So the derivative of a to the x, where a is some base, is equal to a to the x times the natural log of that base. There's a couple conditions on the base. The base needs to be positive and not equal to 1. If it was equal to 1, you wouldn't have an exponential function. 1 to the x is just 1, and the derivative of 1 would be 0. Now, this formula really encompasses e to the x, but we usually like to think of e to the x separately. The derivative of e to the x, if you really wanted to, you could say is e to the x times the natural log of the base. What's the natural log of e? 1. So yeah, this formula works, but we usually just say, oh, really? The derivative of e to the x is just equal to e to the x. So this first formula up here is the very general formula for any base, like 6 or 2 or 17. I should say any positive base. Whereas this is the one that's probably going to come. Cool. We got time. So, words. There's so many things to say. All right. Yeah. Sorry. I want to say all the things. But... So let's talk about the product rule, which is really why I want to talk. So the product rule. So I want to find the derivative of x squared times sine of x. I'm going to point out it is not equal to 2x times cosine of x. You cannot, as I said before, just take the derivative of each part and multiply it together. In the same sort of way, it's why the derivative of, say, like x cubed times x to the fourth is not equal to 3x squared times 4x cubed. Because we know that x cubed times x to the fourth is what? If I simplify it. What's x cubed times x to the fourth? Yeah, and what's the derivative of x to the seventh? Which is definitely not 12x to the fifth. So I really want to point out, just to emphasize one more time, we cannot take the derivative of a product by getting the product of the derivative. Doesn't ever work. Or it rarely ever works, and it only ever works sometimes because you have weird special situations where you just happen to have functions that happen to work. But it almost never works, so you shouldn't do it. Okay, so what do we do instead? Well, we do the product rule. So here's how the product rule works. I want to take the derivative of f of x times g of x. You may or may not want to write this down because I am going to show you how it works. And I'm going to use the limit definition. I'm going to say, okay, well, that's going to be the limit. H goes to 0 of, here's how people often do this. They often say, I'm going to call this f of x times g of x just for a minute. I'm going to call this capital F of x. Because it bothers them to write that. So I'm going to write this as the limit h goes to 0 of capital F of x plus h minus capital F of x all over h. I honestly couldn't tell you why people do it this way. They just do. So then capital F of x plus h is really little f of x plus h times little g of x plus h. I get the limit as h goes to 0 of little f of x plus h times g of x plus h minus little f of x times g of x. I don't know why we couldn't just jump straight to that. But okay. All right, here's where the magic happens. We're going to do a trick. It's a math trick, not a magic trick, but it's still a trick. We're going to add and subtract something to make it work out the way we want it to work out. And really, how would you know to do this? Because someone else showed you the answer before. I don't know who, someone came up with this somewhere. I don't know how. I probably should be able to actually know how they came up with it and learn about it, but I'm not sure what gave them the inspiration. Here's what we're going to do. leave yourself some room. Okay, f of x plus h times g of x plus h. And then way over here, we're going to have minus f of x times g of x. And in the middle, I'm going to subtract and add the same thing. I'm going to subtract, what am I going to subtract here? And f of, I have to actually make sure I get it right. Sorry. I'm like, which thing am I subtracting here? That. This doesn't really matter which I do. F of x plus h times g of x. And I'm going to add the same thing. F of x plus h times g of x. I haven't changed it, right? It's still the same thing when you add and subtract the same thing. But now we're going to break this up into two fractions. I'm going to break it up into this piece over h and this piece over h. And I will point out that in that first piece, I can factor out an f of x plus h. I'm going to have the limit as h goes to 0 of f of x plus h times, I'm left with g of x plus h minus g of x all over h. Plus, here, I can factor out a g of x. And I'm going to have g of x times f of x plus h minus f of x all over h. Okay, so now we're going to let h go to 0 and watch what happens. If h goes to 0, I get f of x plus 0. Well, that's just f of x. Okay, here's the big question. If I take the limit as h goes to 0 of g of x plus h minus g of x all over h, what is that the limit definition of? I wrote up here, limit as h goes to 0, g of x plus h minus g of x all over h. You all would tell me that I'm taking, oh, sorry, you can't say that. You all would tell me I'm taking the what of g of x? Or to the d. It's the derivative. That is the limit definition of the derivative of g of x. So we can say, oh, that's g prime of x. And that's kind of the point. Is that when you take the limit of this as h goes to 0, you get g prime of x plus g of x times, okay, essentially the same question here, everybody. What's the limit as h goes to 0 of f of x plus h minus f of x all over h? F prime of x. And I've probably written this in maybe the opposite order that most people write it in. That's okay. It doesn't really matter because the order of multiplication, the order of addition doesn't actually matter. You can add in any order and multiply in any order and still get the same result. But here's the end result. The product rule says the following. If you take the derivative of f of x times g of x, you get f times g prime plus f prime times g, or as it's usually written, f prime of x times g of x plus f of x times g prime of x. What I usually think, it's the derivative of one piece times the not derivative of the other piece plus, and then you switch it. You do the derivative of the other piece times the not derivative of the other piece. So now back to these examples here, and we have enough time. Yes, we'll finish this out here. So just to point out, I could use the product rule, although it'd be silly, but I'm going to just to prove a point. I can use the product rule to take the derivative of x cubed times x to the 4th. It's going to be the derivative of the first piece times the not derivative of the second piece, plus switch it up. Leave the first piece alone, multiply by the derivative of the second piece. So when you do that, you get 3 times x to the 6th plus 4 times x to the 6th, which is 7 times x to the 6th, as expected. So there is some evidence that the product rule really does work. And then to go back to the original question that we were asking about, okay, great. Now I can find the derivative of x squared times sine of x by taking the derivative of the first piece, multiplying by the other piece left alone, plus switch it up. do the opposite derivative you did before. So don't take the derivative of x squared, leave x squared alone, take the derivative of sine, cosine. And there is your derivative of x squared times sine of x using the product rule. And you have to use the product rule to take this derivative. There is no other way to do it. Okay, and it's 259. I guess it's not 5. Let me say actually one last thing. So there is a product rule. The derivative of f times g, very kind of simply written, is f prime g plus f g prime. There's also a product rule for a product of 3 things. So if you want to do f times g times h, the derivative of that, there is a pattern. It's really nice. The pattern is it's always the derivative of one piece times the not derivative of the rest of the pieces, and you have to make sure you get each piece's derivative showing up at least once. So this one would be f prime times the other pieces left alone, plus g prime times the other pieces left alone, plus h prime times the other pieces left alone. And you can actually apply that for any number of things multiplied together that you want. So for example, if I want to take the derivative of, say, f times g times h times k, it doesn't really come up very often, but the reason we're talking about it is because that's something else. It would have, how many pieces added together would it have? Not 2, not 3, but 4, because there's 4 pieces multiplied together. And you would exactly get f prime times the other pieces plus g prime times the other pieces plus h prime times the other pieces plus k prime times the other pieces. And you can do that for a product of 10 things or 100 things or 1,000,000 things. All right, and it should stop there because we're actually out of time. Next Tuesday, we'll continue talking about this. We'll talk about the product rule some more. We'll definitely talk about the quotient rule. We'll talk about the chain. I guess I will just say, just so that if you want to work on the homework, you need about the chain rule. Here's an example of the chain rule, just for your knowledge. The chain rule basically says, if you want to take the derivative of a function of some other more complicated function, you take the derivative of the outside piece. So I've got the derivative of sine of some stuff. Well, I know the derivative of sine of x is cosine of x. So the derivative of sine of some stuff is cosine of that same stuff. But then on the outside, you have to multiply by the derivative of that stuff. So that is the very, very basic example of how the chain rule works. You leave the inside alone, take the derivative of the outer function, but then after you do that, you have to multiply by the derivative of the inner function. So hopefully that'll at least help you get. We'll definitely talk more about the chain rule and more examples on Tuesday. But if you want to start working on the homework, that will help you.